Okay, and I'm back. I had to go and attend a meeting, make sure that my department gets money next semester. So one of the joys of being the department chair is you get drug away to meetings of different committees. So we were talking about plate tectonics at the last time as I ended the last video. Again, this is a drawing of the different types of plate tectonic movement. Fault line is an area where two plates are coming together, one subducting under the other. A trench is sort of the same thing, but trenches tend to be under the ocean, whereas fault lines are on the surface. See faults or ruptures in the earth crust where plates meet. The advanced ridge, one plate plows under the adjacent plate for trenches. Again, you have a ridge, which is a thin spot, but as you'll notice, nothing is coming out here. The magma is being held in place. This is a volcano. And then, of course, hot spots is an area where you have a little small sort of continuous eruption. Volcanoes tend to erupt rather violently, as we've all seen on the television or in the news. A ridge, excuse me, a hot spot here. These sort of continuously put out magma. It's not a violent eruption. It's more like a leaking pipe. This is like a dam bursting. This is like a leak in a pipe in your yard, and it just slowly is letting the magma come out. Again, we got Gondwana and Pangaea. We mentioned those earlier. Here's Gondwana land. If you'll notice, all of the landforms are all together. You got this one little one here. Then it begins to split up. You have Pangaea, which is here, and it's going to be made up mostly of North and South America. Some parts of some other islands as well are here. And then you see over the next several millions of years, things take their current position. You see here how closely, you look right here, this is part of Europe. This is Africa, and that is South America. That's Australia and all the little islands around Australia. That's the Indian supercontinent, which will eventually come up and join Asia right there, slamming into Asia, uplifting what are called the Himalayas. I learned Himalayas. I was taught that they were the Himalayan mountains. Recently on some television shows, I have heard that mountain range being called the Himalayas. So whichever. The big tall mountains where Mount Everest is where India and Asia combine. And then, of course, we have what the Earth looks like today. Similar sequence of sedimentary rock layers exist around the world, so we're putting time into perspective. This is another one of those things that can cause some controversy. As you start moving down these layers, you go back in time. But there are areas of the world where that crust has literally been flipped. So when you go down in those areas, you're actually coming forward in time. But we have to be real careful about looking at rock layers and saying, are they sitting as they were deposited, or have they been folded? You can actually see this when you cross the 430 bridge going back into Little Rock from North Little Rock, or going into North Little Rock from Little Rock. In the area where they cut through that hillside, you got a big sort of a bluff over here and a bluff over here, and the road cuts through. Now, don't do this if you're driving. If you're driving, don't do this. But if you're a passenger in a car, as you're going by there, turn and look, and you can see where the layers of rock have been folded. They're literally, the layers of rock go up and come down because what was at one point a flat surface has been squeezed and it's called uplift, and it's been uplifted. And so that can cause some problems when looking at layers. But the transition between layers mark boundaries of great intervals of time in the geologic time scale, and each layer's composition will give us clues about what Earth looked like during that particular time frame when the layer was deposited. I'm sure you all have heard at some point that some area that is now desert used to be the bottom of an ocean. Well, this is how we make that determination. We look at the composition of those layers. And if you're in the middle of the desert, but the rock layer shows you that right here, this rock layer is full of seashells, well, at some time, in some way, there must have been some sea life there. So, and this is the Grand Canyon, I'm sure. That's the one we usually show. No, this is the Coconino sandstone, which stretches from California to Montana. It's mainly weathered sand. Has ripple marks and reptile tracks, are the only fossils in it, and many think it is the remains of a vast sand desert like the Sahara Desert today. So you see all of these different layers show different fossils. You get up here, this is going to be the newest stuff. As you move down, you get older and older and older. And this, again, I know you can't see this very well, but it's in your textbook. If you open up the slide presentation in Blackboard as well, you can see these with more detail. And on each layer, you're going to find a different set of fossils. Similarities in structure of body parts are often evidence of a common ancestor. We refer to these anytime different organisms, let's say different animals, have similar structures. We call these things homologous structures. Similar body parts that share and that reflect a shared ancestry. May be used for different purposes in different groups, but the same genes direct their development. And the example they usually show for this, and I'm going to say this and then flip the slide, and it's not going to be that, but it's usually the front or top limb of vertebrates. A body part that appears very different in appearance, but may be quite similar in underlying aspect of form. Again, they appear different, but they may be similar in underlying aspects, evidence of a shared ancestry. Morphological divergence is where patterns of evolution of a body part changes with its descendants. There we go. I knew it would be here. Originally, the forelimb of vertebrates. This is simply saying, and again, this is theoretical, that this is what the original stem reptile, the reptile that gave rise to all of these different organisms. Again, don't get disturbed when you see human beings and reptiles mentioned. But if you look at the formation, we have one bone here, we have two bones here, we have a collection of bones here, and then we have 5 digits. Well, let's look at a pterosaur. A pterosaur is the soaring dinosaurs. They're not technically dinosaurs, but we won't quibble. But you see one bone, 2 bones, a collection of bones, and then 1, 2, 3, 4 digits. This is a wing. A chicken, you see 1 bone, 2 bones, another collection of bones, and then 1, 2, 3 bones. This is the chicken wing. Penguin, another bird. 1, 2, collection, and then the finger bones. The porpoise, again, now, see, all of these, see, we have 5 in our original. We have 4 here, 4 fingers. We have 3 fingers. We have 3 fingers. Well, fingers can sometimes, the bones can sort of merge during evolution, or if they're sort of in the way, they can be lost during evolution. That's why we went down to 3 here and here. But if you'll notice, all of these mammals all have 5. But if you look here, here's the 1 bone, and remember, porpoises have flippers. You know, you've seen the dolphins waving. This is the structure they'll wave. There's the 1 bone, there's the 2 bone, there's the collection of bones, and there's 1, 2, 3, 4, 5 digits. The bat, so this one, what's this used for? Swimming. What's this one used for? Actually, these are used for not so much swimming, but for direction and steering in their swimming. and of course for waving at SeaWorld. The bat, the structure is used for flight. You have the one bone, two bones here, and then 1, 2, 3, 4, 5. There will be skin stretched between all of those to form a wing. There's skin stretched over all of those to where the porpoise can swim. There's the human arm, one bone, two bones, collection of bones, 1, 2, 3, 4, 5. And you get this. These bones right here on the human hand, that's these bones here. The collection of bones is your wrist. And then, of course, we have the elephant. Again, what's this one used for? Reaching, grabbing, picking things up. The elephant, the front limb, used for walking. One bone, two bones. There's the collection of bones. And then 1, 2, 3, 4. 1, 2, 3, 4, 5 digits. So, divergence in the vertebrate forelimbs, all with the same basic structure, but for a multitude of different purposes. Some body parts look alike in different lineages, but did not evolve in common ancestry. These are called analogous structures. Think about the wings of a bat and the wing of a butterfly. Those are analogous structures. The wings on a bat and the wings on a chicken are homologous structure, but on the bat and the butterfly, analogous structures. Similar structures that evolved separately in different lineages. So the wing in the bat evolved one way, and the wing in the butterfly evolved a different. An evolutionary pattern in which similar body parts evolved separately during different lineages is called morphological convergence. They get to the same place, they converge, but they got there from different starting points. That is morphological convergence. And again, here we start convergence in the wing. There's the wing on the bird, the wing on the bat, and the wing on the butterfly. Again, ancient common ancestry. We have a division here. Don't know what happened here, but you have this, and then ultimately insects form wings. And then we have this lineage. Again, don't get irritated about this. This is simply mammals, and this is non-mammals. See, there's the bat, and there's the limbs with 5 digits. Ultimately, we get the bat with the wing, and then we get the bird with the wing there. Neutral mutations accumulate in DNA at a predictable rate. Lineages that diverged recently have more nucleotide sequences in common than ones that diverged long ago. What that says is, where there is a common gene, and the one most often talked about is the cytochrome C gene. The cytochrome C gene is a gene that is present in all carbon-based life on this planet. It's a wave metabolism. It's one of the it's one of the genes that gives rise to one of the proteins or one of the enzymes that makes the electron transport chain work. All life on this planet has a cytochrome C gene, but the human cytochrome C gene is different from the tiger cytochrome C gene. And the tiger cytochrome C gene is different than the butterfly cytochrome C gene. And the more closely, or the more similar, that's a better word, those cytochrome C genes are, the shorter amount of time, since there's differences in mitochondrial DNA sequences between maternally related individuals are due to mutations, not genetic recombination during fertilization. So, when we talk about mitochondrial DNA, we look at the mitochondrial DNA between different human beings. Mitochondrial DNA is inherited along the maternal lines, and we see any differences between human beings. That is due to a mutation, not some genetic recombination. So if my children's mitochondrial DNA is different from my mother's mitochondrial DNA, that difference is not because of recombination that occurred during meiosis. It's because of a difference it's because of a mutation that occurred between mine and my children. So I have what my mother had, but if mine mutates, when I pass it on to my children's will be different. Embryos of related species tend to develop in similar ways. This is one of the things that got some of the early researchers into evolution in trouble. They took pictures of early embryos, and in the early days of photography, when you're taking pictures of very, very small things, the detail wasn't very good. And what these gentlemen did, and I believe, this is just me, this is my opinion, I think they did this with the best of intentions, is they touched up their pictures. They, and again, I'm not a photographer, I don't know about processing video, but I know you can take the negative and you can sort of paint the edges of the edges, so the edges of the negative, so things are clearer. And that's what they did. They took their pictures were kind of fuzzy, and they, using photographic techniques, and it's called retouching, they fixed it. It's kind of like when you go in to have your photo made, and nowadays they take a picture of you and they go in with Photoshop and remove the shadow or remove the scar, or you've got a big pimple right here, they cover over the pimple. That's called retouching. And we do that all the time. If you go to, a professional photographer and he takes your family's pictures, before he prints them, he's going to fix them. He's going to retouch them. He's going to, if he knows what he's doing, he's going to use Photoshop or some other technique to take out any imperfections. And that is what these gentlemen did. They fixed their pictures. But then the people who were anti-evolution, when they reported, they said, well, these pictures were created. They made these pictures. Well, no, they took the pictures and they retouched them. But by doing that retouching and not really saying that they had done it, not putting a little asterisk by it and say, picture has been photographically retouched to show detail or something like that. They just simply published their pictures. So then the people who don't believe in evolution simply said, well, you just created those pictures. You made those pictures happen. It's like the pictures that you've seen of the black moth sitting on the tree that has the lichens on it, and the lichen-colored moth sitting on the tree with the dead lichen. And the people say, well, how did you take those pictures? And the guy said, well, I took a moth and I stuck it on that tree. Oh, so you created it. That's not, you didn't take a picture of what's actually happening. Well, how many times can you take a picture of a moth sitting on the side of a tree? What the guy did was he took a dead moth and said, this is what happens. When the lichen's covering the tree and the black moth lands there, the bird can see it and the bird eats it. When the lichen dies, the brown moth is now not as visible, but the white moth, the moth that was the color of the lichen. So they changed. And again, without saying that I actually did that. That's why if you ever watch a TV show and they have a little thing at the end, say the images are either actual or created, yeah, that's what they're telling you, that they may have manipulated this situation so it shows what it is. This is still what's happening. But it's hard to take a picture of a moth landing on the side of a tree. But you can see it, but before you can get your camera up, the moth moves. So similarities and pattern of embryological development are the result of master genes, those homeotic genes we talked about earlier, that have been conserved over evolutionary time. Differences in the adult form are brought about by variations in the master gene expression. Again, we talked about earlier that HOX-C6 gene in eyes. This is comparison of different embryos of different vertebrates. Again, if you open up the PowerPoint presentation, there's probably a note down here telling you what each one of these are. I'm going to look. Let's see, embryological stages, staging system for the short-tailed fruit bat. A model organization, order, blah, 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 blah. Okay, so I'm guessing what this is saying is this is the formation of this fruit bat from here as it continues to develop. This looks like the HOX-6 gene. Again, not sure what that creature is going to be. I'd be almost willing to bet you that's a snake of some sort, but you see the eye forming there. You don't see much of an eye forming yet there. Again, very, you can kind of look at that and see that there are some similarities. Actually, if you saw this much earlier, it would look more like this. What information does it provide about different lineages? A missing link fossil. A missing link fossil would show you, okay, let's say for instance, again, let's talk about human evolution, which is the one that's most controversial. The early proto-humans, even though they stood up, they were very bent over, and then we got to the ones straightened up. Well, the missing link would be the one that shows all of the human characteristics, all of the modern human characteristics, jaws, skulls, vertebrae, and all of those things. Evidence is essential to scientific theories. The evidence that led to this theory of evolution is all fossil evidence. And again, that's why it's incomplete. It's always going to be incomplete. There was a very famous early evolutionary thought researcher who said, and I'm not going to tell you, we're not going to worry about his name right at the moment, but he said, until I find a modern rabbit in the stomach of a Tyrannosaurus, evolutionary theory is the only one that fits. Because regardless of what you may hear and what you may see on the internet, there are no trackways that show where a dinosaur walked through a marsh and left footprints, and 5 minutes later, there's a series of tracks where a human walked through there. That does not exist. Nothing like that has ever been found. Have there been dinosaur footprints and human footprints found next to each other? Yes, but they weren't laid down at the same time. They were laid down millions of years apart. And the reason they are there is because the dinosaur fossil formed and then was covered over, and then a human walked by the dinosaur fossils and left their footprints, and the human footprints are about this deep and the dinosaur fossils are this deep. They were not laid down at the same time. They were laid down millions of years apart, but just in the same place. If you have any questions, trussell@uaptc.edu. Also, you could reach me through the contact tab on Blackboard course messenger link. If you have not completed exam 2, please let me know. I believe it closed this past Sunday evening. If any of you need me to reopen it for a couple of days so you can take advantage, I'm willing to be flexible since we were out of school for almost 2 complete weeks due to the snow event. So just let me know if you need me to do that for you. I'll be happy to.